second video for Chapter 10, I want to talk about satellite motion. Satellite motion, I think, is really interesting, especially since we did just launch more men, not from Russia this time, but actually from Florida, from the United States, using the SpaceX rocket up to the International Space Station, which is currently a satellite. It's in low Earth orbit. I want to just do a quick recap on circular motion because we didn't study that whole chapter. But I just want to remind you, in order to move in a circle, you have to be in a state of constant acceleration. The reason you're constantly accelerating, even if you're moving at a constant speed, so we want constant speed in a circle. Now, all satellites don't move at constant speeds in a circle. Some satellites actually move with speeds that vary a little bit, and they move in a path called an ellipse. But we're going to start with this idea, constant speed in a circle. So the direction of the velocity is continuously changing. There's something that's pulling it into the circle. That's a force towards the center. We call that a centripetal force. When we're talking about satellites, the centripetal force is caused by gravity. We have a gravitational force towards the center. If this was planet Earth, and this is a satellite of some sort, and planet Earth is really much bigger. Let me redraw that. This is planet Earth, and perhaps this is a satellite orbiting the Earth. The centripetal force is caused by the gravitational attraction. The object's weight provides that centripetal force that causes it to move towards the center. When the object's over here, its velocity doesn't have to change, but now our gravitational force points this way. So we have a continuous centripetal acceleration and a continuous centripetal force, and that force in this case, when we're talking about satellites, is gravity. Gravity is the force that causes satellite motion. Now, we're going to really look at why we go into orbit instead of just falling and crashing into the Earth. Okay, suppose that you build a tall tower up on top of the Earth. Here's my tall tower. And from this tall tower, I'm going to try and launch a satellite. If I shoot it horizontally, its path looks something like this. That's a horizontal projectile. If I shoot it a little bit faster, its path looks something like this. If I shoot it even faster, its path looks something like this. But if I shoot it faster still, its path looks like it never gets any closer to the Earth. The Earth continues to curve, it continues to curve, but it never gets any closer. If we're very, very close to Earth, what we know is if you go straight out 8,000 meters, the Earth drops 5 meters. That's the curvature of the Earth. For every 8,000 meters you go straight out, the Earth is going to drop 5 meters. So, if you're somewhere close to the Earth where the acceleration due to gravity is 10 meters per second squared, we know you fall 5 meters in that first second. Well, if you're going 8,000 meters per second, you're going to travel 8,000 meters horizontally, you're going to drop 5 meters, you're not going to be any closer to the Earth than you were a minute ago. And if you go another 8,000 meters, you're still going to drop another 5 meters. You're not getting any closer to the Earth because you have such a high tangential velocity. When you have a velocity that doesn't point towards the sun, that's called a tangential velocity. If your tangential velocity is fast enough, you can fall towards the Earth without ever getting any closer. So the moon is in free fall, the International Space Station is in free fall, all of those satellites that are up there, GPS satellites, military satellites, they're all orbiting the Earth in a state of free fall. Okay, if you are orbiting and you are in a circular orbit, first of all, one thing we know is that you are going to be traveling at a constant speed. Not a constant velocity because your direction is always changing. So a constant speed. You're not going to be speeding up or slowing down. We know that in satellite motion that the direction of the speed is perpendicular to the gravitational force. So if you're moving in an orbit like this, in a circle, you'll be moving like this, but the gravitational force is like this. And those are going to be at right angles to each other, no matter where. If I'm right here, the velocity is going to point like this, but the gravitational force is going to point like that. It's going to be right angles. If we use some trig vocabulary, we say the velocity is tangent to the circle, and we say the acceleration or the force is radial along the radius. It points towards the center. Another word for that is centripetal. So this is a centripetal force or a radial force. It points along the radius. But the velocity is tangent to the circle. We know that for low Earth, close to the Earth, it takes about 90 minutes to make an orbit. The International Space Station is in low Earth orbit. It's about 200 miles above the Earth. That doesn't sound that low, but it really is. And it orbits about 90 minutes. It's going about 17,000 meters per second, I think. I'd have to fact check me on that, but I believe that's how fast it's going. The moon, however, is actually going much slower. At higher altitudes, you can go slower. For one thing, when you're at a higher altitude, you're making a much, much larger circle. The moon, we know, orbits with a period of about 28 days. The period is the time for a complete orbit. So the period of the International Space Station is about 90 minutes. The period of the moon is about 28 days. There are some satellites that are what we call geosynchronous. When you look up, they always appear to be in the exact same spot, and that's because they are above the equator, and they rotate once every 24 hours. Well, if your period is 24 hours, and the Earth spins once every 24 hours, those geosynchronous satellites appear to never move because they always look to be above the exact same spot geographically. So what are requirements to get into orbit? Let's make sure we know what's absolutely necessary. First of all, in order to go into orbit, you have to have a sufficient tangential that minimum tangential velocity is usually around 8,000 kilometers. about 8 kilometers per second, or about 8,000 meters per second. Some things are orbiting faster. If you get farther enough away, they're going to go slower, but you've got to have that high tangential speed. You also normally want to get above the atmosphere. The ISS is largely above Earth's atmosphere, but it's not completely. Even the ISS has some minimal air drag to overcome. And the way they overcome it is they have to periodically use one of their little booster rockets to just kind of adjust their speed so that they stay in orbit. If there's no air drag and you have sufficient tangential speed, you will stay in orbit indefinitely. You'll just be like in free fall forever. Every time you get fall 5 meters, the Earth falls away 5 meters, you're not any closer than you used to be. So a satellite is just a very, very high-speed projectile. There are some things that don't orbit in circles. In fact, there's quite a few things. They orbit in what we call elliptical orbits. An ellipse is just an oval shape, but it does have two, we call them plural for focus. There's two individual focuses, but the plural is actually foci, or foci, depending on whether you think it should be a hard C or a soft C. What happens is, with planets, when they orbit around the sun, there's the two focus. The sun will be at one of them. When you are in an elliptical orbit, you do not have a constant speed. Generally, in order to get into an elliptical orbit, you have to launch at a speed greater or slightly less even than needed for a circular orbit. So at a particular height, there's a particular speed that puts you into a circular orbit. Well, if you're at that altitude and you're going a little bit too fast, let's suppose you're here and you're going just a little bit too fast. Well, instead of going in a circle, you go a little bit farther. But your gravity will start slowing you down. And you'll go slower, 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 slower. And then as you get closer to the, let's say this is the sun, as we get closer to the sun, gravity gets stronger when so it starts going faster, 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 faster. If we looked at this, you're faster over here. And I'm talking in this case about maybe a planet orbiting the sun. Faster when closer. And you're slower over here when you're farther away. You're slower when farther. Okay, so what we just learned is if we're in an elliptical orbit, we will not have a constant speed. We will speed up and slow down continuously if something's traveling in an elliptical orbit. If you have something that's in an elliptical orbit about the Earth, then the Earth would be the thing at one of these two focus points. Okay? But whatever's the center of the orbit, one of them will be located at one of the two focal points, or the foci. All right. Elliptical orbits are a really interesting idea. For a very long time, the assumption was everything in the heavens, all the stars, all the planets, what they literally called heavenly bodies, moved in perfect circles. They felt like God would have made the universe with the perfect shape of a perfect circle. So it was a little unsettling when Kepler came along and we realized things don't move in perfect circles. Kepler came up Just like Newton came up with 3 laws of motion, Kepler took information and he came up with 3 laws of planetary motion. The first law basically says that the path of the planets is an ellipse. That was a big surprise. Everybody thought that even once we got past the geocentric theory, we thought it was heliocentric and everything orbited the sun. The assumption was that it orbited the sun in perfect circles. But what Kepler discovered by looking at data, lots and lots of measurements made by a man named Tycho Brahe, who was, Kepler was one of Tycho Brahe's students. He determined that the path of the planets were actually ellipses, and the sun was at one of the focal points. So the path looks something like this. And if there's 2 focal points, one of them is the sun. So maybe this is a planet orbiting the sun. So the path of the planets is an ellipse. The sun is at one focal point. An ellipse has 2. One of them is going to be there. That's the first law. That's all the first law says, is that the path or the orbits are elliptical and the sun is at one of the focal points. The second one has to do with how fast everything is going. Sometimes this is called the law of equal areas. If I sweep out, let's suppose the sun goes from here to here, and that's a certain amount of time. And then another point, the sun goes from here to here in the same amount of time. There's A, B, there's C, D. If it takes the same amount of time to go from A to B as it takes to go from C to D, those are equal areas. A planet will, what they call, sweep out an equal area in the same amount of time. Notice it will look even different over here. What's that tell us? Well, if all 3 of these are equal areas, it's going fastest right here because it's covering that distance in the same amount of time that it covers this distance. The fallout is that it's moving faster when it's closest to the sun, and it's moving slowest when it's furthest away. If I were to draw a straight line, this point right here, the very closest point, would be the very fastest point. Similarly, if I go straight over here, that would be the very slowest point. So it's not traveling. As it gets closer, it's speeding up, speeding up, speeding up, speeding up. It swoops down. Now it starts slowing down, gravity's slowing it down, slowing. And then as it moves back towards, it's getting closer, speeding up, speeding up, speeding up, speeding up. Second law, it sweeps out equal areas in equal amounts of time. The third law is probably the one that you will do the least with. And the third law has to do with the relationship between the radius of the orbit, which is how close it is, and the period. And the third law says, basically, that the square of the period is proportional to the cube of the radius. Or, if you wanted to rearrange that, you could say the square of the radius divided by the square of the period divided by the cube of the radius is going to equal a constant. Let me draw a picture of the solar system. Let me write that up here. If this is the sun, And you've got some planets sweeping out ellipses, and farther planets sweeping out different ellipses, and planets farther still sweeping out different ellipses. What they're saying is, as this radius increases, the average distance from the sun, that's what the radius is that they're talking about, as this number gets larger and larger, the period of the orbit also gets larger. But it's not a direct proportion, because the square of the period is actually directly related to the cube of the radius. But as the radius increases, so does the time it takes to lap the sun. Well, that makes sense. If you talk about a planet like Venus, which is farther from the sun than the Earth is, it makes sense that it takes Venus a longer time to make a lap. Mercury, which is closest to the sun, makes that lap pretty quickly. Okay, so the closer you are to the sun, the faster your orbit is, and the shorter that period is going to be. All right, conservation of energy. Remember, things in satellites that are in orbit, the only force that's acting on them is gravity, and gravity is a conservative force. We don't lose mechanical energy because of gravity. We lose mechanical energy because of friction. That's a non-conservative. But gravity doesn't cost us anything. So what happens if we're in a circular orbit? Let's just think about a satellite orbiting the Earth. This distance is always the same when you're in a circular orbit. If you're in for a circle, the gravitational potential energy is constant. You're not getting any closer to the Earth, you're not getting any farther away from the Earth. If you're in a circular orbit and move at a constant speed, your gravitational potential energy is constant. If you're going at a constant speed, your kinetic energy is constant. Of course, those things put together means that your mechanical energy is constant, which is exactly what we expect. All right, but what if you're not in a circular orbit? If you're not in a circular orbit, your speed is changing. And your kinetic energy is changing because your speed's changing. And if you're farther from the Earth, your gravitational potential energy is changing. So let's look at what happens. Let's look at an ellipse. We're in an elliptical orbit. And I'm going to put the object here, kind of exaggerated it a little bit. When you're close, at point A, that's your closest point to the Earth. Let's say you're orbiting the Earth. Maybe you're a weather satellite, but you're up there in an elliptical orbit. At point A, your GPE, that's your gravitational potential energy, is at its minimum. Why is it at its minimum? Because it's the closest to the Earth. We know as we get farther away from the surface of the Earth, we have a gravitational potential energy will go up. The farther we are from the Earth, the more gravitational potential energy we have. However, when we're closest, that's when we're going faster. The kinetic energy is at its maximum value. Those two add up to give you the mechanical energy. So that's at point A. Let's go to point B. What happens? Well, since we are farther from the Earth, notice our distance has increased. We were this far. Now we're this far. So at point B, the GPE has increased. Why did it increase? We got farther away from the surface of the Earth. However, the kinetic energy has decreased. Why did it decrease? As we get farther away from the Earth, the orbit slows down. Those still add up to this. These two are going to be equal. We're not going to lose any mechanical energy. We're going to gain some gravitational potential energy, but we're going to lose some kinetic energy. By the time we get all the way over here, where we are at our farthest distance, I'm going to call that point C. At point C, you can see that the gravitational potential energy is at its max. That is the farthest distance from this Earth that this particular satellite will ever be. It's considerably farther away, so we've had a pretty substantial increase in gravitational potential energy. However, when we are farthest away, we are going the slowest speed. So our kinetic energy is at a minimum. And again, if you add those together, we get the same amount. So the total mechanical energy at point A and point B and point C is always the same. But as we are slowing down, we're losing kinetic energy and gaining gravitational potential energy. On the way back around this way, we're losing gravitational potential energy and we're gaining kinetic energy. So elliptical orbits and circular orbits both have conservation of energy. But in a circular orbit, there's no change in gravitational potential energy. There's no change in kinetic energy. They stay constant all the time. With an ellipse, you need to remember, as you get farther away from the planet you're orbiting, if it's the sun, farther away from the sun, you are increasing gravitational potential energy. But as you get farther away, you're decreasing kinetic energy. If you're getting closer, it's exactly the opposite. As you get closer and closer to the Earth, you're decreasing your gravitational potential energy, but you'll be traveling faster and faster, and that's going to increase your kinetic energy. Okay, there's one more idea that you may have heard of that we have not talked about, and that's the idea of escape velocity. Can you travel fast enough to escape Earth's gravity? And the answer to that is yes. If we want to launch a satellite into circular orbit, we already have said that minimum speed near Earth is about 8 kilometers per second. 8 kilometers is 8,000 meters per second. If you go a little bit faster, let's think about this. So that gives us a circle. But what if you accidentally launch too fast? Well, if you launch too fast, you're going to make an ellipse because you were going just a little too fast. When you go a little too fast, you're going to make an ellipse. But if you go way too fast, you can actually reach a point where you're just going to leave. It's going to continue to get farther and farther away. Now, it will slow down. Remember, as you get farther away from the Earth, the acceleration of gravity is still pulling on you and pulling on you. It will gradually slow you down, but it won't ever make you stop and turn around and come back. That's the difference. In an elliptical orbit, it slows you down till you turn around and come back. What's the minimum speed? Escape velocity is 11.2 kilometers per second. That's 11,200 meters per second. So we actually, if we're talking about near Earth orbit, we have kind of a window. We have to go 8 kilometers per second to get that circular orbit. We go a little too fast, we'll get an ellipse. But if we were to go this fast, rather than get an ellipse, we could actually escape Earth's gravity. It would move farther and farther away. Mechanical energy would be a constant. The farther away it went, what we would see is GPE would be continually increasing, and kinetic energy would be continuously decreasing. It would gradually slow down, and it would be going slower and slower, but it would still continue to move away from the Earth. So it wouldn't maintain this 11,200 meters per second the whole time, but nevertheless, it would always be in a situation where it would continue to move away from the Earth. That's my discussion of satellite motion. Remember, satellites really like projectile motion, except it's going so fast, it's a high-speed projectile, that it never gets any closer to the Earth. As always, if you have questions, please email me, come to our meeting, ask questions. I'd love to hear more questions during meetings.